Welcome to Calculus. Today we will investigate how to integrate improper integrals. We'll take a look at 4 examples. Our first example is to determine whether each integral is improper, and if it is improper, to state the reason. And I've got 3 potential integrals here. So let's define for ourselves what an improper integral is. There's basically two possibilities for an improper integral. One of the possibilities is that one of the limits of integration is infinite. So we would say an integral is improper if one or both of the limits of integration are infinite. So that tells us in one view what would make an improper integral. We have a second set of qualifications that would make an integral improper, and that's if it has a finite. So if the integrand has a finite number of infinite discontinuities within the closed interval from a to b. So if an integrand shows this finite number of infinite discontinuities in the closed interval from a to b, we would say it's an improper integral. Or if one or both of the limits of integration are infinite, we would say it's an improper integral. So that said, I'm going to look at these 3 examples. And initially, the easiest way to identify an improper integral is to find an infinity in one of those upper or lower limits of integration. So among these 3, the one that I could immediately identify as improper is number 1 here. And that's because it's got the upper limit as infinity. Now, looking at the other 2, neither of those has limits of integration that are infinite. So then I'm going to consider, does either number 2 or 3 have infinite discontinuities? So as I look at the integrand for number 2, x cubed is the cubic function, which is perfectly continuous across its whole domain from negative infinity to positive infinity. So this is a proper integral. It's got finite limits of integration, and there's no infinite discontinuities, in this case, between 0 to 5. So then investigating this third integral, this graph, or the integrand 1 over x minus 1, has a vertical discontinuity, infinite vertical discontinuity at positive 1. And so definitely that's in this interval from 0 to 3. And so what I would claim for this third one is that is also improper, but for the second reason. It's got a finite number of infinite discontinuities in its closed interval from a to b. Now, we make that judgment call about whether it's a proper or improper integral so that I can have a strategy in place if it is improper. Our second example is definitely an improper integral because its upper limit of integration is infinity. So what I want to do then is I want to determine whether or not the improper integral converges or diverges. And if it converges, we want to find its value. So what we'll do is let's set this up, let's integrate, and then we'll see the convergence or the divergence at the end when we go to evaluate. So if I've got an integration like this one, number 7, from 1 to infinity of 1 over x cubed dx, what I want to do is I want to rewrite this by replacing this upper limit, could have been the lower one, whatever one is infinite, with its variable. So I'm going to say that this is equivalent to I'll leave a little space. The integration from 1, which would be my a, to b of 1 over x cubed dx. But what I want to say out here in front is that I'm really taking the limit as b approaches infinity. So initially what we do is we just switch out the infinite limited integration with a limit out front. So what I want to do now is I want to actually evaluate this. So I'm going to take the integration of 1 over x cubed. So remember, I can think that's x to the power of -3 dx. So looking for an antiderivative, that's going to be x to the -½ but then that's going to come down as a -1 over 2. And that would ensure that when I differentiate, it would get me back to x to the -3 dx. So we're going to evaluate. This is the limit as b approaches infinity of -½ times, we'll put it back in its positive power, 1 over x to the power of +2, evaluated from 1 to b. So now I want to treat it just like I normally would with a definite integral. I want to evaluate by fundamental theorem of calculus. So I'll just put limit as b approaches infinity. Then I'm going to plug in these values. So this is going to be equivalent to -½ times 1 over b squared minus -½ times 1 over 1 squared. So now we're ready to evaluate the limit. So this is the limit as b approaches infinity. And what I see for this first term, in fact, what I can do is get rid of that limit because we're ready to evaluate. So for this first term, if I have b going to infinity in the denominator, and in fact it's squared, 1 divided by infinity squared is going to become 0. And 0 times ½ is going to 0 out. So that first term becomes 0. And then this second product becomes -½ so that's +½ times 1 over 1 squared is 1. 0 plus ½ is ½ And so what we see is that if I'm able to evaluate the limit, that is a sign of convergence. I would say that this limit or this integral converges. If the limit did not exist, then I would say that that integral diverges. So you make the call about convergence, divergence at the very end as you're evaluating the limit. So this one converged, and its upper limit was the one that was infinite. Our second example has the lower limit as an infinite limit. So for this one, I've got the integration from -∞ to -1 of 4 over x dx. And so just like with our previous example, I'm going to start by rewriting this as the integration from a to -1. So I'm just swapping out my infinite limit of integration with the variable. And I'll put 4 over x dx. I don't change the integrand at all. And then out front, I do need to put that this is the limit as a approaches -infinity. So now we're ready to integrate. And I need to think about this 4 over x. One thing I can do here is allow that 4 to migrate outside the integration. So it's the limit as a approaches -infinity of 4 times the integration of from a to -1 of 1 over x dx. So I do that because that really makes that integration visible. If I've got or a derivative of 1 over x dx. The antiderivative is going to be the natural log of x. So let's integrate here. This is going to be equivalent now to the limit as a approaches negative infinity of 4 times the natural log of x evaluated from a to -1. So now we'll apply the fundamental theorem of calculus to evaluate a definite integral. So it's the limit as a approaches negative infinity of 4 times natural log. In fact, this is going to be absolute value. So natural log of the absolute value of -1. And then I'll just pick up minus natural log absolute value of a. So at this point, I can evaluate the natural log of absolute value of -1. That's natural log of 1, e to the power of 0 is 1, so that has a value of 0. So this is 4 times 0 minus natural log, if I'm taking the limit as a approaches negative infinity, the natural logarithm function as x goes to infinity, y is also going to infinity. So that becomes infinite. And at that point, what I would claim is that this limit does not exist. And therefore, the claim that I make about the improper integral is that it diverges. If the limit at the end does not exist, we would say that the entire integral diverges. Our last example is of the sort that it's not got infinite limits of integration. Notice it's the integration from 0 to 1 of 1 over x cubed. But what I see is that this 1 over x cubed has an infinite discontinuity at 0. If I plug in 0, 1 over 0 cubed is undefined. That's a vertical asymptote on that graph. And so for this type of improper integral, when it's not improper because of the limits of integration being infinite, but because there's an infinite discontinuity in the interval from a to b, what I want to do is set up a one-sided limit. So I'm going to rewrite this one as the limit as a approaches 0 from the right. We're saying from the right because our interval is from 0 to 1. So where we're approaching this, that the 0 is on the left side, so we're approaching it from the right. And I want to rewrite the integral from a to 1 of 1 over x cubed dx. So that's how you would set up one of these improper integrals that's improper because of a infinite discontinuity. Once you got it set up, we're going to do the same integration. So this is equal to the limit as a approaches 0 from the right. And then just thinking about 1 over x cubed dx as an integrand, what I can call that is x to the power of -3 dx, and then searching for an antiderivative, that would have been x to the power of -2. But then I need a factor of -½ out front to cancel the coefficient. So as I integrate now, this is going to be equivalent to -½ times x to the power of -2. And in fact, what I'll write that as is as 1 over x to the power of +2. And we're evaluating that from a to 1. So now let's evaluate the limit. In fact, before we evaluate the limit, we're going to set this up according to the fundamental theorem of calculus. So this is going to be equivalent to -1/2 times 1/1 squared, plugging in the upper limit of integration, minus -1/2 times 1/a squared. And again, what I want to do is start evaluating. So here, I see that this is going to be -1/2 times 1/1 squared is -1/2 times 1, or just -1/2 minus. So then I'm going to get -1/2 times 1/a, and a is getting closer and closer to 0. So I can imagine that that denominator has a smaller and smaller number in it. So it's the opposite of dividing by infinity. Dividing by infinity would tend towards 0. Dividing by something getting close to 0 would be infinite. So this is really +1/2 times infinity. And again, what I've got to say is that that is a limit that does not exist. It's infinite. And therefore, again, what I would claim about the original improper integral is that it diverges. Thanks for joining for this investigation of integrating improper integrals. See you soon.